Here we go. We'll begin with a word of prayer. Dear Father, we thank you for this day. Again, I thank you for these students. Just ask you to help us use this time wisely, Lord. In your name I pray. Amen. So, I guess this is a complex analysis help session, the first ever. You feel this is? I mean, you're part of something important, new. You know, first ever, the inaugural. Can I say inaugural? I could not say for the life of me time elapsed. Oh, now I can't say it again. ELAPSED. I'm not even going to try. It's outside my, I can't say it. So do you guys have questions? Yeah, go for it.
So for problem 12, this was the one that said do 1, 4, 6, and 7 of page 28.
All right.
And it was about describing like interior boundaries, if that is open or closed.
Right.
If it's connected and all that.
Oh, yes,
so
yes.
1 and 7, of course, have answers in the book, but those I didn't really have any trouble with doing.
Uh-huh.
But I guess the question is just like how to go about doing the other ones.
Do you want to talk? I could take a stab at D, number 4. Did I assign that one?
Yes.
Okay, but I'll still look at it because, I think it might be helpful. Actually, it might be helpful for me. I didn't do C, right?
No.
Let's look at C briefly, and then we'll try to understand D. We'll do C as a warm-up. So C is the set. It's the set of complex numbers, right? Good grief. X plus IY, such that what? Such that x squared is less than y. And we're asked just this laundry list of questions. Describe the interior and the boundary. State whether the set is open or closed, or neither open nor closed. And state whether the interior of the set is connected if it has an interior. This is a very, they're asking us a lot, aren't they? But so the way I think about something like this is just draw a picture. And that's all I want you guys to do for these problems, really, is just to draw a decent picture. And so the equation, y equals to x squared, well, that's a parabola, right? Badly drawn, but there you go, parabola. And we're saying, and I kind of rather look at that as y, right, y on that side. For some reason it helps me. I don't know what's wrong with me. Y greater than x squared, right? I know it's stupid, but just for some reason, if it helps me to write it that way. So this is y equals to x squared in the green, right? So the solution set to that inequality are the points above, right? Up in here. So that's what C. That's a rough picture of C. And so what were and this is not included, right? Yeah, thank you. So, generically speaking, here's just an intuition for things. If the set has fuzzy edges, then it's open, right? Because that means that if you take any point in the set, right, no matter how close it is to that edge, you can find a little open disk around there which doesn't go outside the set and is contained in the set, and consequently that point's an interior point. So in fact, every point in C is interior, so I can say that the interior of C is actually equal to C. Every point is interior. Every point in C is interior. What other questions were we asked? What are the boundary points?
Describe the interior and the boundaries, say whether it's open or closed or neither.
All right.
See if it's connected.
So first of all, if it's equal to its interior, that implies it's open. So C is open. The boundary of C is the green curve I had just drawn, right? So how do I know that that's the boundary? Well, pick any point on the parabola, right? Like this one. And no matter what open disk you draw around it, there's points inside and outside the disk, right? Out, in. So that makes that point, P is an element of the boundary of C. And so the boundary of C, in this case, you can see geometrically, it's, Z is equal to x plus iy, such that y equals x squared. I mean, you could write it various other ways, but there's a way to describe the boundary as a point set.
So if it was just a
You could use a sentence. You could say that the set of points on the parabola is the boundary. That would also be fine with me in this particular problem.
So like if the set was what we have for the boundary of this C, if that was the set.
If the C was defined by equality rather than inequality, it would just be the parabola, and that would certainly not be. That would definitely not be an open set. I mean, a curve is not an open set in the usual. Well, I can't say that universally. There are these annoying things called space-filling curves. You can find a curve which covers every single possible point in the unit square. So I don't know.
So does it have an interior?
But if we just think about this, right? If you think about any point on there, is it an interior point? Well, no, because if I take any, is that inside the curve, inside that set? No, if that's the set, if this is the set, then that's outside. I mean, that's not, every point is not interior. In fact, every point is a boundary point. So for a curve, the boundary of the curve is the curve itself. As long as the curve is a familiar curve and not some kind of weirdo space-filling curve, which is, less familiar and would lack other nice properties. But anyway.
Because I think that's kind of how number 4 is.
Oh, you think D is like that? D is, what is it? It's Z such that...
Such that the real component of Z squared equals 4. So I said that meant that x squared minus y squared equals 4.
Let's see here. So we've got Z squared is x plus iy times x plus iy. I feel like I've done this calculation 10 times this week. X squared minus y squared plus 2ixy. So the real part of Z squared is what did you say?
X squared minus y squared.
X squared minus y squared. Right. Yeah.
And so then that equals 4. And so that just gives you like...
What is that? Yeah.
Hyperbola?
Right. Yeah, that gives you a hyperbola.
So it's just like two long curves.
Two curves, yeah. So, nope, not open. Is it closed?
Yeah.
Yeah, it is closed. Every point is a boundary point.
And it doesn't have any
Wait, that's not the
interior.
definition of closed, is it? What's the definition of closed?
It contains its boundary.
Contains its boundary points. So, yeah, U is closed if the boundary of U is a subset of U. Right. An alternative definition of closed, which is also useful to know about, there's another way of looking at closed. U is closed in C if C with U removed is open. In other words, a set is closed if its complement is open. So if you think about taking a curve and deleting it from the complex plane, it leaves you like the complex plane with a fuzzy edge sort of cut in the middle of it, and every point is interior. But I do like that it contains its boundaries, also a very good definition and helpful to us here.
So is that curve its interior? Or does it not have it?
The interior is empty.
So it doesn't have it.
Doesn't have an interior. There is no interior point.
Okay. Oh, right.
Because the interior is the set of interior points. So, I mean, there's some part of us that wants to say, well, the whole curve is its interior. I can see why you'd want to say that, but that's just not the definition. Definition of interior is set of interior points, since no point on the curve is interior, in the sense that there exists an open disk around it contained in the set. Yeah. Did we also ask it about connected, right? No?
It said, is the interior connected if it has an interior?
Oh, okay. Never mind. Yeah, fine. Yeah, okay.
How
This one or that one?
That one on the left.
Well, here's a point. Here's a point. Yep.
Is there any way to do that formally?
Oh, you want to make it
Go on
complicated.
like this way.
You don't need to do it, I'm just wondering, like,
What would be involved? All right, let's get into it. Let's get nuts. So pick 2 points, all right? Let P1 and P2 be in C, right? The interior of C, which is, okay, great. Then P1 is equal to, x1 plus iy1, and P2 is equal to x2 plus iy2. If x1 equals to x2, then, P1, P2 is a vertical line segment. I mean, what does it look like? It's with typical point, would the typical point be in there? Something like x1 plus I t times y2 minus y1, right? These such that 0 less than or equal to t less than or equal to 1. That's the definition of the line segment. It's the line segment that has starting point P1 and ending point P2. And I'm assuming x1 is equal to x2 for a moment, right? So can you prove that every point in there is in C? What would be needed? Because you'd like to show that, to show that P1 and P2 are connected. I mean, to show that C is connected is to show that any 2 points in C can have a path between them. Now, technically, you can use a broken polygonal path, right? But in practice here, a line segment will do, yeah?
Right, so you just move in the vertical direction and then move
Right.
over.
But like you said, let's get technical. So how do you, what is required then? We need to know that the P1 to P2 is actually a subset of C.
Right.
So what test does it have to meet? We need to know that,
Every point on the segment
yeah, so we need like x1 squared is less than t times the difference of the y's, yeah? I think that's the condition that needs to be met for it to be in C, right? But of course, we also know that x1 squared is less than y2, one squared is less than y1. That's given because we're assuming that those points are in C. So we have those. You'd have to use those to prove that inequality. Having proved that inequality, then you would have established that the vertical line segments. And then I would suppose x1 is not equal to x2. And I would say, okay, well then without loss of generality, x1 is less than x2. Then I would build the line segment from those 2 points and show that that line segment was in subset. Now, my bifurcation of the argument into the case x1 equal to x2 and x1 not equal to x2 may or may not be necessary, but that's just my kind of knee-jerk reaction to how to carefully prove it. But for you guys, this was part of the point of this help session, that picture in a sentence saying a line segment, it's possible to draw a line segment between any 2 points in this shape that's clear geometrically. It is clear geometrically. But what's clear geometrically may be an awful mess to actually prove with this kind of argumentation. Yeah. I know of no such set in the complex plane.
Okay, one that is algebraically difficult to figure out.
Well, that I would love to help you with. Algebraically difficult to figure out. That is exactly why we're here. Now, there may come a time where I'd like to actually see these kinds of details, but in that case, the problem will come with extra language, like, please carefully show that this set is path connected, right? If I just say, like I'm trying to say now to supplement my instructions, you can draw a picture for that problem, you know. Really, what I'm trying to get from you here is not the ability to give picky, these kinds of arguments. It's to draw pictures and gain an appreciation for what complex equations mean in terms of, you know, direct visualization. So, okay, let's get back to it. Which one are you having trouble with?
Solve the algebra word.
Ay, caramba.
I'm not sure if it's right, but that was the first thing I thought to try.
Well, let's see, how can I say this? If it's right, it's still wrong. Let's see here, -4 equal to 0. And I'll tell you why. I mean, it might be right. Okay, so set that aside for a second. Something easier. Suppose you're given the set S, z equal to x plus iy, such that z squared minus 3z plus 2 equal to 0. Right? Great. Now, this is z minus 1 times z minus 2 equal to 0. In other words, this set is extremely silly. I mean, I've written this set in a rather silly way, because this set is just what? How can you have the product of this and that be 0 in the complex number system? Right. So this is just the set containing 1 and 2. So what's the picture? So there you go. That's S. Is it open? Nope. Is it connected? Nope. Is it closed? Yep. Can I say anything else about it? I don't know. Now, oh, hey, fun side comment. If this is a hyperbolic equation, so much worse. Because we can have the product of non-zero things be 0. So you have, you'd also be allowed to look at things like z minus 1 is 1 plus j, and z minus 2 is 1 minus j. And you'd get solutions other than 1, 1, 2. If I had to wager a guess, I would say that in the hyperbolics, the solution might well be, and this is conjecture on my part, but my suspicion is that the solution is like this. If I had to guess. But I'm just speculating. And this is not your current homework, right? I kept it complex, didn't I? So I kept the homework complicated, which you guys appreciated. Well, except for that first problem, but that first problem is actually kind of not that bad, is it? No. Okay, so that one, if you factor, I think is 3 points. Wait, how do I know it can be factored? That's a polynomial, third order polynomial equation. Fundamental theorem of algebra says that has 3 solutions, possibly repeated. They exist. That is a set of 3 points.
One of which happens to be 1.
If one of them's 1, then I can factor it. Or minus 1? Oh, it's got 1 and minus 1?
No, it was one or the other. I'm not sure.
Oh. So let's see here. Oh, we just plug it in. 1 minus 2 plus 5 minus 4. I think we need a minus 1. Minus 1 minus 2 is minus 3. Oh no, wait a minute. Is 1? I can't do math. Yeah, 1. 1 works. But the factor is z minus 1. Because 1 is a root. If you plug in 1, you get 6 from here and minus 6 from there, which gives us 0, which means z minus 1 is a factor by the factor theorem. And then you can, of course, just look at it, right? So z squared is not up for grabs, and plus 4 is not up for grabs. So you just got to figure out what goes here. Minus z. It's got to be minus z because that gives me a plus z and a plus 4z, which gives me a 5z, and I got a minus z squared and a minus z squared minus 2z squared. Yep. Yeah. So. Or you could do long division rather than guessing.
Is there an analog to the rational roots theorem when you're working with complexes?
I don't know. Is
But
there?
sometimes it's
I mean,
pick them out, you know?
I mean, the rational roots theorem is still relevant here,
Right.
but because rational roots are complex roots. Yeah. And that is a, real coefficient. I mean, that polynomial is basically playing by all the same rules of the game that we set forth in college algebra or high school algebra or middle school algebra as it ought to be. But I'm joking, I think. Did you have a question? No? Ah, okay, that's cool.
So then,
Is there another problem in here that would be helpful for me to do? Did I assign you guys?
well, that's
Mhm.
what I asked about.
Oh, okay, go for it.
That's still then just points?
Yeah, it's a set of 3 points,
Okay.
which is not open. It is
You don't
closed.
have to like find what they are or anything, you can just look at that and say, oh, it's 3 points, so.
Oh, no, I think it's healthy for you to find the other 2 points. I mean, there's 1 and complete the square.
But like you don't have to like draw a picture.
Drawing a picture would be healthy. I mean, the other points, 1/2 plus or minus 4 minus, whatever that is. Square root of 15 over something, I don't know. I don't think the imaginary component to that point is particularly pretty, but it's not. I mean, you could complete the square on the green thing, right? It's not a big deal. But yeah, I mean, on the flip side of things, if you're pressed for time and just want to say, like, what's going to happen, I respect that as well. But this is homework. So you have unlimited time. This will be reflected in my course evaluations, I know. All right. Do you have any other questions about these particular formulas in here? I mean,
I don't think so.
did
The
I?
main question was just like if it was just a line. What
Did I assign? I thought 15 looked interesting, but I haven't. Let's try to work number 15 in here if you guys don't mind. Unless you have something else that you want me to do.
I don't necessarily know how to tell some star shape.
Ah.
Unless it's just the same thing, like draw a picture and look at it.
Well, yeah, it's draw a picture and look at it. And if we want to, I mean, that's the first level. Draw a picture and look at it, give a geometric argument. If you're going to say something's not star-shaped, you need to give some kind of, I mean, it's really, to prove something's not star-shaped is to prove that there's no possible star center, right? To prove something's star-shaped, it suffices to find one star center that works. It doesn't have to be unique.
Do you just show it algebraically, or can you just draw a picture?
You can just draw a picture for this. It's fine. I'm trying to be gentle. I mean, it's a healthy thing to try to give the picky subset is this, the lines. So, all right, here, for example, slit complex plane, this guy. All right, this is what I called C minus, I think. So what we're talking about is C minus the negative real axis, yeah? So if I can, I don't know, it goes on and on, right? I'm just drawing the thing that's missing, so let me just put a box to make a picture, okay? So it's clear to show that this is not star-shaped, right? First of all, it's clear that if you pick anything up here, you can't get over here without crossing the divide. So nothing in the second quadrant is a possible star center. Likewise, nothing in the third quadrant is a possible star center. It's then also easy to see that anything in the positive first or you know, the proper, not including the axis, first or fourth quadrants can't be star centers, right? Because if you do something down here, if you do something down here, there's no way you can get here, right? And no way you can get here. So like I would not try to draw pictures. I would say this in sentences. I would use words to communicate that. So I would say, so it follows that the only possible star center must lie on the positive x-axis by process of elimination. So let's consider that case. See, because that doesn't follow the same arguments. The other, like this, it's about crossing. It's about crossing. This one is not about crossing. It's about something else. If this is a, you know, so pick any, you know, any, let's say r comma 0, which we, of course we could write as just r in 0 to infinity, and I argue that that's not a star center. Wait a minute.
I'm thinking that it is.
Maybe I'm wrong. Maybe I'm wrong.
I think it is.
Maybe I'm wrong. Yeah, I think I'm wrong. Because if you pick, yeah, I think I'm an idiot. Right. If you pick any point over here, you can get to it, right? And I was worried that you could somehow get caught up on the slit, right? But you can't, because the slit is actually, I mean, a more honest picture of it is, you know, I don't know how to make an honest picture of it. It's a mathematical line that's been deleted. So, you know, if I did it right, you can always, you never hit it. The only way you will intersect the dotted line is if you're actually horizontal. If I did the picture exactly right. I mean, so, and these points right here, right? Well, you can get to those just by the horizontal line, and that's not a problem. And you can, I mean, you can get everywhere. So in fact, any point on the positive real axis serves as a star center for the slit complex plane. Maybe it's helpful to think about something that's not. So one of your homework problems, and it's kind of subtle, but I'll draw a picture for it. One of them works out to like this. I was talking to somebody earlier. If I did it right, it's like, you know, it's like a circle and a half plane. So you're looking at something like this, you know. And the set is actually all of this, you know. I really miss chalkboards sometimes. This is one of those times. And so, you know, it's fairly obvious that the star, anything except the dividing symmetry line here is not going to serve as a star center, because you're not going to get, like, not going to be able to go, you know, if I pick something down here, it's fairly clear that I can't reach there without going outside. Oops, right? And so if you just start thinking about it, the only reasonable place to hope there's a star center is like right here, right? But, you know, why is that not a star center? Well, that has to do just geometry, right? This is a circle, badly drawn, and you know, it's going to hit that tangent like that, and you see you're never, ever going to be able to get this little deficit of points right there. They're not reached. Here's a more pragmatic example that we'll see later in the course. Something like this, an annulus, right? Not star-shaped, right? So like the best case you can hope for is maybe to put the star center like right here, right? And then you just start thinking about it, well, right? So there's like some sort of maximal, I don't know what you want to call it, the maximal star closure for a given star center. I don't know what this is called, but you can see that you can't get to the lower points in the annulus without leaving the annulus. So this is not star-shaped. And here you could give an argument by symmetry. Consider that point, and you could consider points along a diameter. And then, if you can come up with an argument for each such point that's convincing, then you can say, but by symmetry, if we can't do it for that diameter, we can't do it for any diameter. I think that's kind of but again, proof by picture for us is fine. Yeah. Let's look at number 15. I think that might be healthy. I almost assigned that as homework. So maybe it's a good problem. Or maybe we'll all be glad that I didn't assign it as homework after we look at it for 3 minutes. Let's see what the case is going to be. Number 15. So number 15, we've got omega 1, region omega 1, z, such that, what do we got? 1 less than modulus of z less than length of z between 1 and 2, and the real part of z greater than minus 1/2. And then we got ourselves an omega 2, which is what? Z such that 1 less than modulus length of z less than 2. And the real part of z is less than 1/2. All right. We're asked to show that both omega 1 and omega 2 are domains, but omega 1 intersect omega 2 is not. Let's see here. So both of these are actually within an annulus, right? So what is this? This would be, one out from the origin, right? So this dotted line I just drew, this is, modulus of z equal to 1. The unit circle, yeah? And 2, well, that's circle radius 2, yeah? Seems like a good job for a protractor. Wait a minute, no, compass, what I'm thinking. Compass, idiot. Sadness. Anyway, 2, radius 2. So this is, z equals to 2 out there. So both omega 1 and omega 2 are subsets of, they're both subject to this condition. They're both in this, this annular region. Now, omega 1, what does it say about our z? Now, if z is equal to x plus iy, the real part of z is x. The imaginary part of z is y. So omega 1, we've got the real part of z is greater than minus 1/2. So here's x equals to minus 1/2. So omega 1 is actually this more than half circle, right? So if I ask my child to break a cookie in 2, the green part is the part they will take. All right. And then, and so again, that's my omega 1. What's omega 2? Right. X equal to 1/2, so omega 2, real part less than 1/2. Omega 2 is this other. So if the cookie broke in half on the red divided line, my child would choose the red shaded portion. All right, to be clear. You missed the exciting part. So we were just talking about eating cookies and such, but anyway, so there's omega 1, there's omega 2. What happens when you take the intersection? What's the intersection of omega 1 and omega 2? Omega 1 intersect omega 2, that means we're looking at where all three conditions are met, and that's just this right here, right? And this down here. What are we asked in this problem? A few different things. We're asked to show that they're both domains, but that the intersection is not. What is a domain? What's domain mean? Domain equals open and connected subset of, well, for us at the moment, C. Now, the red shaded region and the green shaded region were both connected. They're not star-shaped, right? But they are connected. They're connected because if I pick this point, right, and I take this point, both in omega 2, right, I can do this. I can go, wah, 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 wah. See, there's a broken polygonal path going from one point to another point, even no matter where they are in omega 2. So omega 2 is connected, and it's also open because each point is interior. You're not really expected to prove that. I mean, to actually prove that would be 2 pages of picky stuff. Now, you might take a graduate class later where you're actually expected to prove that. That might be the point of that class, you know, that you gain that kind of, well, maybe as an act of vengeance for when it was done to them, I don't know. But I just want you guys to understand these terms, and it's okay if we use a little bit of geometric reasoning. Yeah. So, okay, so omega 1 is clearly a domain, omega 2 is clearly a domain because they're open, they're path connected. But omega 1 intersect omega 2, well, it is open. See the blue region? It's still got fuzzy edges, right? It's open. Every point in the blue region you can draw a little disk around it that's still in the blue region, but it's not connected because I can't take a path that goes from a point like this point and that point. I cannot connect them with a path inside the blue region. I have to leave. And it's also the case, another way to look at so there's 2 different ways to look at connected, guys. So this is not connected, all right? So the reasoning I just used in the brown, I just basically said that it's not path connected, right? But there's a more like fundamental definition of connectedness in topology, which says that a set is connected if it does not allow a separation. What's a separation of a set? A separation of a set is if you have set S and it's equal to U1 union U2, where U1 intersect U2 is empty and U1, U2 are open, if you can do that, that's called a separation of the set. And the more general definition of connected in topology is that a set is connected if it does not allow a separation. Those 2 blue regions, that's a separation because the upper region union the bottom region is the totality of omega 1 intersect omega 2, and their intersection is quite clearly empty. So, yeah. But I know, I like path. I mean, the path-connected definition is good for us in here. But, you know, some of you are interested in topology. It's good for us to say a word or two about it in the abstract. And also, this other way of thinking about connected actually appears meaningfully and technically in a proof later in the course. Because you like look at a set of things, you show that if this set of things you're looking at existed and had something if it had something in it, it would provide a separation, which is impossible because like the given thing you're looking at is connected. That ends up being a proof later on, kind of as a surprising thing. I forget where it was. I just know it's in the, I remember giving this proof, but it was 2015, so you know. I don't remember where it was exactly. Sorry about that. We've got, when does this thing go to? What do we decide? 4:10, right, so we have 15 minutes left. Are there any of these, you know, geometric complex problems you'd like me to fiddle around with? Did I assign you guys 19? I'll just say in words what I think these sets are. Part A, we have modulus of z minus 1 less than 2, or z plus 1 less than 2. Those are two circles. And, oh, I looked at them earlier. They're overlapping. It's like you took two of the Olympic circles. So, B, that's actually what I was talking about over here. It's outside the unit circle and positive reals. So that's like a half plane with a bite taken out of it. Kind of hungry. C, we have that the modulus of z is greater than 1. This is sometimes called an exterior annulus. So if you just have the modulus of z is greater than 1, what's that look like? Actually, let's say modulus of z minus z naught is greater than r. I'll make it more exciting. There we go. Arbitrary center, arbitrary radius. So you draw a picture. Whoop, 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 whoop. Here's your z naught. Here's your radius, whatever that is. Right? And what that condition says about z is that the distance from z to z naught is larger than r. Geometrically, that just means you're outside that circle. So like z is out here. So if you're looking at such a set, we sometimes call this an annulus with one of the radii at infinity. Or sometimes it's called an exterior annulus. Or sometimes you can just call it everything outside a circle, if you like that. I mean, whatever language floats your boat. Or outside a disk, yeah. These things come up. And then part D, we've got x positive and then two linear inequalities. So I would just remind you that to graph linear inequalities, you should graph like where the equality is attained, and then think about whether you're above or below the line. I'm not sure what exactly this looks like, but I'm not sure. I shouldn't hazard a guess. I mean, you should be able to draw lines. You know, something like one of the inequalities is like this, right? Maybe another of the inequalities is like this. So the common solution, and maybe the other condition is that x is positive, I don't know. So if you put all those three things together, where all of them are true is what the set is, if it's defined in terms of and. So like the green would be something like the thing you're looking at. Oh, but it's not, well, the language is a little bit different. X is positive and that or that. So it's not what I said. It's not an and logic, it's an or logic. It's a combination, actually. It's got x positive and either, oh, how to say this? Let me try something similar. If I had this set S, and it was x plus iy, such that x is greater than 0, and then he gives like brackets, y is less than 3x plus 1, or y is greater than x. Like that would be a similar but uglier problem than the one that's given. So in brackets, let's see here. So that would look something like y greater than x, or in other words, x is less than y, right? So y equals x is this guy. We're saying x is less, so that's down here, right? That's the last inequality I drew. And then the y is less than 3x plus 1, or y is less than 3x plus 1. That's this guy. That's, yeah.
The other way around.
But you know what? To make this interesting, well, I don't know, like this is kind of dumb because the first inequality supersedes the second, like for where we're interested in for positive x. In other words, if you're below this line, right, you're automatically, I see how to say this, that or that, right?
Isn't it above? Wait, if y is greater than x?
Oh, y is greater than, I'm sorry, y is greater than x. Thank you. Good night. Yes. But, so, think about that. It's or, right? Or. So it's the union. So like, this one is like a these. Up and 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 up, right? And how about the other one, the 3x, y is less than 3x plus 1? Well, that's like a these. Right? And then when you tack on this guy right here, that puts a hard line right there, right? And goodness, it looks to me like that's a really stupid way of writing the half plane. Like I'm pretty sure that this is just equal to z in C such that the real part of z is positive. Yeah? Yeah. Hopefully the problem that you're given in the homework is more interesting than the one I just made up. But that's the kind of thinking you need to do there. Does anybody have a copy of the mission that I can just look at for a second, see if I can think of any other helpful hints while I'm at it? Thank you. Let's see here. Now, what I've been saying about pictures does not apply to problem 18. Problem 18, I want to actually see arguments for. So problem 18, you're supposed to map a horizontal strip under the complex exponential. That's what problem 20, exercise 23 from page 55. So there you actually need to like it's kind of an onto question, you know, given that the alleged target space produced for me the point in the domain which maps to it. There you're actually going to, picture is not going to be the solution to number 18. It's going to be actual calculations. I will help you out with problem 19 right now. Problem 20, don't ignore my hint there. That's not an easy thing to prove. It's not impossible. Maybe some of you would get it. I don't know, but when I wrote notes for Calculus 1 and I wrote my own proof for the product rule for limits, I found that was very challenging. It took me some time. I'm not the greatest analyst either, but man, that there's something difficult about problem 20. But I think if you follow the hint, it's not that hard. But if you ignore the hint, it will get hard. or if you misuse the hint, I suppose. Problem 19, though, I think it might be helpful to draw a picture. And let me give you kind of a sketch of how I would prove it. So in problem 19, you're given domains D1 and D2, right? Did I ask you guys to prove that the union of open sets is open? I should have done that. That's a good problem. If U1 and U2 are open subsets of Rn, then U1 union U2 is open. It's very silly, right? Notice if X is an element of U1 union U2, what's that mean? X is an element of U1, or X is an element of U2, right? Thus, there exists epsilon greater than 0 such that B epsilon of X epsilon 1 is a subset of U1, and B epsilon 2 of X is a subset of U2, right? I mean, I'm not wording this the most natural way. The point is, if it's a point in the union, it's either a point in U1 or it's a point in U2. In either case, it's an interior point because we're assuming U1 and U2 is open. So it follows that there's an open ball in the union, right? So the union's open. I mean, to show us that's open, we have to show that there's an open ball around a given point. So my point is, if we have two, that question's about why D1 intersect, or D1 union D2 is a domain, right? And so you're given D1, right? D2, they're open, they're connected, right? My point is the fact that D1 union D2, it's the union of open sets, this is open. So that part of it is pretty easy to show, like, you're supposed to show that D1 union D2 is a domain. So all I'm trying to say at the moment is the fact that it's open is pretty, you shouldn't have a lot of trouble proving that. I kind of just gave it to you, although awkwardly. I'm going to erase it because I don't like it the way I wrote it. Don't hurry, just pick a point and argue that that point must be either in U1 or U2, so there's a ball around it in U1 or there's a ball around it in U2, which is of course also a ball in the union, by definition of union. So what's left to show? That the union's path connected, right? What other condition are you given in this problem? An important condition. Their intersection is non-empty, right? So D1 intersection D2 is non-empty. So what's that mean? That gives you the existence of a point. There exists Z0 in the intersection of D1 and D2, right? Your argument has to be anchored around that point. The existence of that point is what drives the proof here. But, you know, I can draw you a picture of what the rest of it is. So that's your point, you know. And then then you got to think about different possibilities, right? Take a pair of points in D1 union D2. It's either both points are in D1 or both points are, take a pair of points, either both points are in D1, both points are in D2, or one is in D1 and one is in D2, right? And you should be able to argue that there's a path between any of those choices. And consequently, as those choices are exhaustive, D1 union D2 is a domain. That is a sketch of that homework problem. Sorry, I don't want it to be mysterious to you guys. It's not meant to be a hard problem. So what's coming up after this homework is like the differentiability stuff, like, but also complex differentiability, like the Cauchy-Riemann equations and these things. Yeah. So, well, thanks, guys. I think to do the homework and
just like the problems you're assigning us, or like going through the book and trying to do like everything?
I think if you're not comfortable with the complex arithmetic stuff, it's helpful to do extra problems in Fisher, yeah. And I would say work on problems in Fisher. If there's something that confuses you, come talk to me. That's going to be a win for you. I mean, that means you're fixing something that's troubling you, which means you have one less weakness on my test, The other thing I should have said ages ago is that I will allow you guys a sheet of notes for the test in here. Since I'm covering more than complex analysis, it seems fair that I would give you a sheet of notes. I won't give you a sheet of notes. You will give you a sheet of notes, to be more clear. They asked me in physics yesterday, are you going to give me the conversion formulas between miles per hour and meters per second? I'm like, no. But I do let you bring a sheet of notes to the test. So, should you put it on there? I can't say. I don't know. Maybe. It's probably a good idea. Thanks, guys.